Every time. Makes me want to play Mario Kart.
I'm excited because I thought we were going to.
No. Maybe. Oh,
After our AP test, we should.
yeah, maybe sometime. Like maybe the end of this semester if we're done studying. Someone would. I don't know how we would connect it though.
That could be a problem.
Okay.
We can determine the acceleration of the vehicle. That way we get a pass to do it in class.
I was gonna say we could make a physics thing out of it.
If
We'd have to approximate a lot of stuff. But we could turn Mario Kart into physics. I mean, I don't know how authentic the physics are in the game itself.
That's what we're
But yes, we could evaluate that. So today, one, I have homeworks from you guys, right? It was just like 6 problems. Huh? I don't know. Do I? Do I have them from you guys or not? Remember those book problems? I gave you like 5 or 6 of them. Yeah. Didn't I tell you guys? Right? Did you do them?
I don't remember this.
Did you? Joy, did you do them? Makaya, did you do them?
Yeah.
Did nobody else do them?
I tried. What?
The homework.
I did it.
You did?
Yeah.
Okay, I need to collect them. That's fine. I mean, turn in what you got.
Okay.
I tried. I don't know if
I
I got it.
told you guys, right? And I posted it to Classroom.
I tried to video too.
Right?
So,
I did, yeah. Okay, I was
don't
gonna
know
say.
if any of them were right, but I got it.
Okay, that's fine. I was gonna say I didn't forget. I swear I didn't forget. It was just like 6 of them or something.
It was 5.
Huh? 5 of them? It's like 1, 3, 6, 7, 8. Yeah. So whatever you got, I'll take.
Excellent.
No, but I didn't understand if you can I like come in your ears?
Yeah, you can. Yep.
Because I was gonna email you last night, but I left my computer here.
Yeah, that's fine.
You have a phone, don't you, Maggie?
Yeah, but I don't.
Do you want me to? Will your teacher let you go if you just say, "Hey, can I go down to here"?
Yes, Mr. Yes, he's preaching.
Well, I don't know. He might want me to sit there and do test reviews. But I only have like 3 questions.
I know.
Well,
I can't do anything, 'cause he said
If you wait the first part and come down even the second half, that'll work just fine. We'll finish whatever he's got. But yeah, you can. Can I collect anybody that finished it? I'll take what you got.
Here's ours.
I
Okay.
made mine on Google.
You did?
I feel
That's alright.
excluded from the group.
It was ours.
But email me.
I said I feel excluded from the family table. You got your mama and your baby.
Email me and tell me. Just email me one more time. Because I want them in person.
Unless you guys are unless you guys did a whole
Okay. So again, I need you guys to. Again, part of what you told me is you need more practice, and I agree. I didn't give you enough opportunities to actually.
in class.
No. That won't work out again because it's AP. I can't fit my lessons, our labs, learning new material, and practice time all in class. So I'm going to need you guys to do some stuff outside of class. All right? Again, I reminded you, and I posted to Classroom too. You guys aren't submitting on Classroom because you guys can turn it into me. The virtual students, they have to, but I put it on Classroom just so that it's always there. If you're like, oh crap, what problems did Mr. H tell me to do? I'm going to put them there. That way you can reference them. All right? I have some homework 1 to give back from last class. Again, I didn't get too many of them. I think that was yours.
Yeah.
Okay, I didn't. Trevor. No, dang it. You guys are still gonna mess me up. So I'll look at those. Again, if you did turn it in, I want you guys to still do it, especially doing it now, like early. Don't turn it in October 7th. You can still do that and get half credit at least, but it won't do you any good because we'll already have taken the test. So I want you guys to do that to at least get this practice and get some points. So that was the only thing I needed to collect. The next thing I want to do, I have a big stack of papers to hand out to you guys. So, John, the in-class stuff is actually what I'm going to do now. Remember the AP worksheets? Those, I printed out all of them for this unit.
Fun.
That way you have them all right now. I don't have to keep remembering to print them out.
We can do them like all in one night and then turn them.
If you
I mean,
can.
technically,
I'd be extremely impressed if you could do that.
That'd be hard.
Oh, thank you.
I don't think I'm capable of it.
I was barely capable of doing the homework.
Yeah, if I can't even turn it over.
So these you don't be overwhelmed. This is for the whole unit.
Oh, I am 100%.
We're gonna go bit by bit, right? So we're gonna be we're due. I think we'll do 3 of them today because we're a little behind. But the reason I do these are AP's worksheets to draw out specific concepts. So one, it's AP's prep, and so it will help you get the concepts that AP's deems important in this class. It'll help you give some sample answering questions that AP asks you. And 2, they structure them pretty well in terms of topic by topic. So I guess I will time out. How do you want me to view homework as a part of this class? Do you want me to actually grade it and let you know? Or do you want me to give you completion points and we can go through it quickly every day?
Yeah. That one.
You want to do that one?
Yeah. Yeah.
Okay, I can work with that.
Good.
Okay? So to be clear, what we're going to do from now on, I'm still going to give you homeworks periodically, not every day, but sometimes. The reason is I think you guys need extra practice to get familiar with, okay, Mr. H told us all this information. What the heck do I do with it? How do I solve a problem with F equals MA? That's what I want you to do with the homework. That's the reason I'm giving you homework, not to just give you work to do. But what I can do is, say I assign it today, next class you're going to have to show me, right? You're going to have to actually show me like, hey, Mr. H, here's the 10 problems that I did. Don't know if they're right or not, but I did them. Then I can give you points. So I think what I'll do for you guys is literally I'll go old school, like hold up your assignments. I'll see who's got them and just give you points. Then what we can do is we can quickly discuss the answers in class. We'll try not to take too long a time so that we can get to the other topics. But that way you can check your work and be like, oh crap, I missed the first 5 of them. Whoops. Here's the correct answers and how we do them. So we can do that. I can work with that. All right, is that the deal? So if you didn't turn in any of these 2 homeworks, I still need you to do that so that you can at least get half points. If you want a 0, that's your prerogative. I don't want you to have a 0. But at least turn those in to me and I can give you half credit. The rest of the assignments moving forward will be completion. So virtual students, it'll be all the same where I'll assign them. You got to submit them on virtual class or Google Classroom. And I'll go in and say, yep, okay, they completed it. And again, the next class when you watch, we're going to talk about the answers together so you can check your work. But that I can deal with. John?
So we're not turning any of these in, right? Because they're just notes.
Correct. Yep, what I handed out, again, virtual students, there's a PDF on this video as well as on Google Classroom. It's the student workbook. This is AP's workbook of all these different things that you do each unit to practice the main skills. These are in class almost always.
So if
We're
I
gonna-
stapled it, wouldn't be a problem.
Huh?
So if I stapled it, wouldn't be a problem.
Correct. Yep, you can do that. I think, Maggie, you use a binder if you 3-hole punch them. I have a 3-hole punch if you want to use. But just, I want you to have them all. And then in class, I'm going to say, hey, guys, we're going to do worksheet 2A. Well, you just open your book, and the first one is 2.A. Virtual students at home, I'll tell you, hey, we're doing 2A at home. So you can go and look at, here's 2A. All right? Those will predominantly be in class. But I wanted to get them out to you guys so I've almost forgotten to print them before a class a couple times, and so it's easier for me to just get them all to you. You hold on to them, and we'll get them out as we need them. Sound good? We'll tweak that a little bit. Speaking of, we're going to do the first one right now. So we've talked a lot about forces, right? That's what we're digging into now with dynamics. We've learned about kinematics, motion, position, velocity, acceleration. What does position versus time graph look like? How do I calculate projectile motion and how high it goes, how long it's in the air? That's all motion, kinematics. Now we're doing dynamics, which is kinematics, motion, plus forces. We're looking at what causes that motion, what changes that motion. So we've been doing forces, we've done force vectors, right? Breaking the force vector into the x and y components to see what motion happens in the x due to the forces in the x direction, what motion happens in the y direction due to the forces in the y direction. We learned how to resolve, that's what you call it, resolve a force vector into its basic components. We've talked about Newton's first law. What was Newton's first law? Bingo. An object in motion will stay in motion unless a net external force, to be super particular, acts on it. Some force has to act on that object in order to change its motion. It also means that an object that's at rest, it will always stay at rest unless some force acts on it and causes a change in motion and acceleration. We also learned about Newton's second law, didn't we? Remember Newton's second law? Yeah, it was just the equation. It was literally F equals ma.
When are we going to learn the third law?
In a bit. We're going to build up to that. We got a couple days before we get there. So what I'm going to have you guys do is the first worksheet in this student workbook. It's 2.A, and it's relationship between force and acceleration. So they're going to start out simple. And they're going to start out I'm going to just show you the... So yeah, what I want you to do is get started on 2.A. 2.A is giving you a list of, there's 7 trials where they pushed an object. They exerted the same force on different objects with different masses and recorded the acceleration. And what it's asking you to do is take that data and plot for any given mass, what was its acceleration? And we're going to plot acceleration versus mass. So work on plotting those points, and then there's a backside of the page that you can take a look at that goes into the relationship between mass and acceleration. everybody at least get the graph plotted, the data points plotted on the front? Alright, so let's look at this together. This one, literally just plot points. First trial was 2 kilograms of mass and 1.5 meters per second. So they plotted 2 kilograms of mass with 1.5 meters per second. Aiden?
Yeah, I missed one. I was doing the wrong thing.
City movie.
I had to print it front back, otherwise I would have used twice the paper. So yeah, they might not exactly line up like one piece of paper is the worksheet. Yeah, it's on the back side of your cover page, I guess. Sorry, I should have clarified. So when they graph, they're literally just plotting points, right? Whatever mass it had with the corresponding acceleration. You see the trend? What happens as mass increases? What happens to my acceleration?
Decreases.
It goes down, doesn't it? Do you remember the mathematical relationship to describe this relationship? What do we call that? Yeah, inversely proportional. Directly proportional means they change the same. If I increase one, the other increases. If I decrease one, it decreases the other. This situation, as I increase one of my variables, the other variable actually decreases. They do the opposite of each other. If you lead into, like right here, these are examples. Direct relationship. X increases and Y increases. It's a line. Here we have inversely proportional where this is our situation, right? We increased mass, but the acceleration decreased. That's what our graph looks like. If it's to the square of x, as you increase x, y doesn't go up the same. It goes up way more. That's a square relationship, right? To the second power square. And then the square is proportional to x. This would be like the square root of something. So we know as the mass increases, right, our graph, the mass of our object increased, the acceleration decreased. Therefore, we can conclude acceleration is inversely proportional to the mass. Meaning the acceleration does the opposite of what the mass does. An increased mass reduces acceleration. A reduced mass increases acceleration. This one, it was a little weird. You haven't probably seen this much. How would you create a linear relationship? Do you see how you don't have a line? You have a curve. The way that you would make one of them linear is to flip one of them. If you plotted acceleration versus 1 over the mass, you'd create a linear relationship. Or if you did mass versus 1 over acceleration. And the last question I want to focus on, and I want to show you, if I do, what did it say? I want to plot acceleration versus 1 over mass. Right? It should look something like like this. That right? Because this would be 1. Yeah, a low mass. Yeah, it would look like this. Yep. Because if I had a huge mass, it would make a small fraction, right? If my mass was 1,000, this would be 1/1000th, which would be really small, and I would have a small acceleration. So this is what our graph would look like if we plotted acceleration versus 1 over mass. It asks us, what's the physical meaning of the slope? Well, we can figure that out using graph. What is slope equal to? In general, how do you find a slope? Rise over run. You will use this a lot, actually. What's my rise? On my graph, when I go up and down, it's acceleration, isn't it? My rise is acceleration. What's my run?
Mass.
Be more specific. This axis is not mass, but 1 divided by mass. Right? So my run is not mass, but 1 divided by mass. Well, then I can just do algebra, right? I'd multiply by the reciprocal. Can you see that? Right? If I flip this to the numerator, I would have A times m, acceleration times mass. Does that ring a bell? How about if I write it in the other direction? Does that ring a bell? Can you guys see that? I'm sorry. MA. What's that equal to? Where have you seen that before? Yeah. Brody's like, wait, I know Newton's second law is F equals ma. So if I say the slope is equal to ma, the slope is also equal to force. So what you can do is realize that was not a linear relationship. It's not a direct relationship. If you flip one of these variables in this situation, you change it from an inverse proportion to a direct proportion. The direct proportion is acceleration to 1 over m. Say you're given this and you're like, hey, what's the slope mean? Well, just do your math, right? Let the graph tell you. You know rise over run, rearrange the variables, like ma, F equals ma. The slope of acceleration versus 1 over mass gives you the force. Specifically, the net external force that acts on the object to cause the acceleration in the first place. How do we feel about that? It's a little weird, but again, we just use our graph to tell us what we want. You'll have to know how to interpret a graph. If they just gave you this and told you to find the force, you'd have to realize, well, let me check my slope. Yep, that works. That's my force. Any questions about this? Technically, I feel like I disagree with this last part. Let's try doing mass versus 1 over a. If I do mass 1 over a, help me with this, because I was disagreeing with the answer key. My slope is rise over run, isn't it?
Yeah.
So I want m over 1 over a, right? Mass versus 1 over a. Well, rearranging that, don't I still get MA? Am I doing my math wrong? Right, I multiplied by the reciprocal. I would get MA, wouldn't I? Well, the slope is still force. Wouldn't it? So I would disagree with if you plot mass versus 1 over a, you get 1 over force. That's not the slope. I disagree with that. And I can't understand if this is wrong or if I'm missing something. Now, we don't have to worry about it. I just wanted to mention, like, from the way I'm doing my physics, I would disagree with what they conclude, but you don't have to worry too much about that. We'll only focus on that first part. The second one I want you to do, this is also just force and acceleration. All right? This one is more of a word problem. This one is saying, again, this is in the student workbook for Unit 2. It's 2.b, force and acceleration. Saying Angela's standing on a low friction skateboard. If it specifies low friction, what does that mean? Do we consider friction or not? No. It said low friction, which is your hint to say, like, yeah, don't think about friction. It's not a factor. Blake is pushing her, and they're measuring her velocity. So Blake is going to be pushing her with a constant force in 3 different levels, and then letting her go at a certain point in time. Trial 1, Blake's pushing softly for a while and then letting go. Trial 2, he's going to push a medium amount and let go. Trial 3, push like as hard as he can on Angela, who's on this skateboard, and let her go. So the first part is asking you to analyze the data, analyze the graph that you're given. And then it's asking you to make a graph based on a different scenario and analyze a statement. And it's just that one page. Yeah, right? Because trial 1 said the saw. Trial 3 would be. So I would agree with that. Increase. Yeah, that one. That question, when it's asking what the slope is, what physical quantity would the slope of that line equal? Like we talked about, the slope of that line would be force. That question is asking, since the slope is this physical quantity, yeah, because it's velocity time. Slope of velocity time is the change in velocity over time. That's acceleration. Then you can answer the second half of that statement. How do you feel about that first one? So you got 3 trials. Trial 1, he pushes soft. 2, he pushes a little harder. 3, he pushes as hard as he can. The statement you got to fill in is when he pushes harder, the slope of this velocity time, does it go up? Does the slope increase, stay the same, or go down? When he goes from soft, medium, to hard. Yeah, sometimes they are. Mm-hmm. This next one's weird. It's saying, basically, what does the slope equal? Our first big blank is, the slope of this line, what is it equal to? The slope of this line is the change in velocity over the change in time.
Yeah, that's what.
Remember what physical quantity that was? Starts with an A. Yeah, it is. Because acceleration is how your velocity changes over time. So that first big blank is basically equals acceleration. That one's weird. I don't like that phrase. But then the second part is you can answer it based on since the slope equals acceleration. Yeah, that one I don't like. It's too vague. Yes. Or yeah, larger, however you want to put it. Yeah, yeah. Makes sense, Evan?
Yeah. So pretty much just
Okay, it's not quite shorter. It's saying this is soft, medium, and hard push. As Blake is pushing harder, is the slope of this line increasing, decreasing, or staying the same? Yeah, so right here you would put the slope of the velocity time increases.
and then since the slope
This one is weird. What does the slope of a velocity time graph tell us?
supposed to be
Yeah.
No. The slope is rise over run.
right.
So it's how much your velocity changes.
And up here,
Yeah, what is that? What physics concept is that? If I tell you my velocity changes a lot every second. If I step on what? Yeah. Acceleration is literally how your velocity changes.
I don't know
over time.
exactly. Like,
So this first line is since the slope equals acceleration.
Okay.
Is the acceleration larger as they go up or smaller? Larger. The slope increases. The acceleration increases.
All right. Thank you.
Yeah.
Got a better idea.
Okay, good. You guys want to talk about this one?
We need a word bank for like options or something.
So I will concede that a lot of the blanks that they leave are super vague. Some of them are they're set up really well. The leading sentence leads you to be like, oh, crap, how do I complete that statement? Some of them, you're trying to figure out, well, what are you trying to state in the first place? So I'll concede that if it weren't for those, I would really enjoy these, but the first part, the point was, again, I'm sorry that's sort of blurry. I can't clarify it anymore. When Blake is pushing harder, right, this is a soft push, a medium push, and a hard push. As he's pushing harder, the slope of your line increases, right? From soft push to hard push, my slope definitely goes up. It's steeper. So my slope is increasing. Now this one was vague. It was basically wanting you to figure out that, well, the slope is acceleration. Remember we talked about this. The slope of a velocity time graph is telling you, hey, the velocity changes this much in a certain amount of time. That's literally your acceleration. If I'm on the interstate at a dead standstill and I stomp on the gas, my car starts to accelerate. My velocity increases as time goes by. So this one, the slope equals acceleration. We know that's true. And because that's true, the acceleration is larger when he pushes harder. So this was the weird gap in the statement. We know the slope is the acceleration, and as he pushes harder, the slope increases. That means the acceleration increases. When he stops pushing at this point in time, what happens to the velocity? Tell me from the graph. At this moment in time, what happens to my velocity? Literally just tell me from the graph. What's happening to the velocity right there?
Levels up.
Yeah, it levels off. It stops changing. It's the same amount at any given moment. What does that mean about our acceleration?
It stops too.
Yeah. Your motion, your velocity cannot change if you have no acceleration. So when Blake stops pushing, the slope of the velocity time graph is 0. It stops changing. That means that the acceleration has to be 0 because the slope of my velocity time graph equals acceleration. Does that make sense from a force perspective? Does it make sense that she would stop accelerating if Blake stops pushing her? Huh? It doesn't make sense to you? What do you think should happen?
She should
She should keep speeding up?
No. Start, but she's just still
I would agree with you, and I agree that this graph is saying that. This graph is saying the moment Blake stops pushing her, she continues at, say, 10 meters per second. So I would agree, Aiden, that that is what's happening. That's true. As soon as you stop pushing, she just goes at a constant speed. Right? She's not speeding up anymore. She's at a steady speed. Does that make sense from what we know about forces? Let's think about Newton's second law. F equals ma. If Blake stops pushing on her, don't you remove the force? If I have no force on an object, can I have any acceleration? No. Right? Newton's second law is literally F equals ma. If I have no force, if Blake stops pushing on her, my acceleration has to go to 0 in order for this relationship to be true. My mass will always be my mass. I can't eliminate mass. Well, that makes sense. As soon as Blake stops pushing, no more acceleration. Only constant motion. Only a constant velocity. So not only does it make sense from our data in our graph, we can also think about Newton's second law and say, yep, Newton's second law also agrees that physics still works. Have I told you guys the difference between laws and theories? No? This is a huge misconception in science. I'm going to take a moment to explain this. I'll try to come back to it a lot. This equation, this is a law. It is not a theory. The difference between a law and a theory. A law is something about the universe that we observe to be true all the time. If you measure the force and acceleration and mass of an object, they're always related to each other by this equation. We have no idea why it works, and we don't care for a law. A law just says this is true. This is something I observe in reality all the time. I can prove it true experimentally and show you, and that's why I can say that's a law. A theory technically is never true. Theory is what explains why this law is the way it is. Right? If evolution happened to be a law, that is, we could observe it happen. Now, it's hard to observe that. But if we observe that in nature, that's a law. We have no clue how it happens or why, but we know it. We observe it. The theory of evolution attempts to explain why we see this. Right? So hopefully I never try to misspeak. Hopefully I won't misspeak about laws and theories, and I'll try and correct you guys, not because I'm wanting to prove you wrong, but I want you to speak scientifically accurate. A law is something we observe. The theory is trying to explain why that law exists or why that law works. All right, so that's my tangent for the day. The next part Actually, I just want to go here for now. It's saying the students do the same experiment, but now Angela holds 2 textbooks, then 4, and that's just it. So no textbooks, 2 and 4. In this case, Blake is not pushing with different forces. He pushes the same amount every time. You have to draw the velocity time graph. Well, this is the benchmark. It was given that when she holds no textbooks and he pushes with, say, 5 newtons of force, accelerates a lot and then levels off as soon as he stops pushing. Well, what do you expect to happen if she holds more textbooks and he pushes her with the same force? Is she going to be able to accelerate as quickly? No. Why? She has more mass. Go back to Newton's second law. Go back to your equation. If this doesn't change and I increase mass, I have to decrease acceleration in order to equal the same force. Does that make sense? Should also make sense intuitively, right? If I try to push, a cat on a skateboard with a certain amount of force, and then I stand on the skateboard and I tell you, hey, push me with the same force, who's going to accelerate faster? The cat. Cat only weighs like 10 pounds.
My cat weighs too much.
Like 20?
He's obese.
Even if your cat weighed 50 pounds, I weigh 4 times as much as that cat. You better bet that I am not going to accelerate as quickly from the same force as that cat is, because I have way more mass. Then, if we had the same mass, what could we say about our accelerations? It'd be the same.
Hypothetically, it'd be the
Same force, same mass, same acceleration. You guys remember that word inertia? Inertia is mass. Inertia is the resistance to motion or change in motion. I have more inertia than a cat does. Therefore, I resist a change in motion more, aka accelerate much slower than the cat does. Josh, you have a question?
Let's say we were pushing you, and we pushed another object that weighed like half your weight, and we pushed you with twice as much force, then you guys would both at the same speed?
Well, yeah, let's try that.
I'm just making sure that's like, that logic actually lines up.
No, that's a great question. This is what we start with, right? So, Josh, you said twice the mass?
So something like that was like half your mass, and we push at one speed, like with one amount of force, and then.
But I do double the force?
And then we double the force for you, because you would have weighed twice the amount of the object. That makes sense. I don't know. It makes sense in my head.
Oh, so you're saying I start with force times mass acceleration, right? Say the cat.
Like, let's say the cat weighs 100 pounds, and we push the cat at one force, and then we push you at twice that force.
So you push me at twice the force, and I have twice the mass?
Yeah. That would make, like...
Let's solve for acceleration. I want to get it to look just like this to compare force, mass, and acceleration. Well, don't I have 2 on both sides of the equation? Divide by 2, divide by 2. Well, that means this has to be A. So F equals MA. Josh, you're right. If I have an object if I'm twice as massive and you push me at twice the force, we're going to accelerate the same. That's a big cat. That's a huge cat. That's a wild cat. That's something that belongs in a zoo. But Josh is exactly right. That was one of our properties of Newton's second law. Force and mass are directly proportional. To keep the acceleration the same, if I increase my mass, I have to increase my force.
In order to keep acceleration the same.
Yeah. Keep acceleration the same. Increasing my mass means I would have to increase the force. If I decrease my mass, I can decrease my force. That's why it's easier to push the cat a certain acceleration than it would be to push me at that acceleration. Because I have more inertia you got to overcome. So that was a good question. The last part, did you guys capture that the last part of the statement is incorrect? The statement was, after Blake stops pushing, Angela is going to keep traveling at a constant speed for a few seconds before she runs out of force. Then she will decelerate and stop. The last part of her sentence is not true. Almost. Her first part of the statement is true. When Blake stops pushing, Angela will travel at a constant speed. Aiden, that's what you're talking about. As soon as they stop pushing, the velocity stops changing. I have no more force, therefore no acceleration, therefore the velocity doesn't change. It's just stuck at whatever it is. So the first part of her statement is true. Why is her second part wrong? She says for a few seconds, she'll go at a constant speed, and then she'll run out of force and eventually decelerate and stop. Why is that false? Brody's exactly right. He said she is not being acted on by any outside force. Blake stopped pushing. There's no more force. We said it was a frictionless skateboard. So friction doesn't slow us down. So if this statement were true, that would beg the question, what on earth is possibly acting on her? There's literally no other forces that are slowing her down.
Gravity.
But there's no friction, so gravity can't create friction. But yeah, Brody's exactly right. That's why this is wrong.
You can't have friction without gravity.
Correct.
Shoot.
We talk about friction in this unit. It's related to the normal force, which is related to the gravity force.
Wait, but how does if I drop a penny off the desk and hits the floor, how does friction have anything to do with that? Friction didn't stop at the floor, did it?
Well, that's like a contact force. That's pushing.
Yeah, that's what I was saying. So you said
Friction is sliding stuff.
yeah, but you said you can't have but at least what I interpreted is that you have to have friction, you have to have gravity in order for friction to work.
Yes, you do. You do. In this case, gravity's still there, but there's no friction on the skateboard. So even though gravity could shove down, it rolls so well that friction doesn't count. It's a fake scenario. You never have a frictionless surface. Ever. Technically, outer space, floating through space, is the only frictionless motion. And even then, as soon as you impact, if there's a couple random particles or rocks that you run into, that's friction. It slows your motion down. But anyway. So they restated, one, you reaffirm, hey, we're neglecting friction. That's something that we're assuming isn't involved in our calculation because it said low friction. It said Angela will continue at a constant speed after Blake stops pushing. That's true. But her velocity will not change until a net external force changes it, aka friction via air resistance. If that were considered, that would slow her down. If she hit a wall,
It could still be stopped by something other than friction, though. If she ran into something.
Yes. Yes.
Sorry, I was busy writing something down, so I wasn't really trying to get off.
Which last part?
I thought drop it. You just said.
What were you saying?
That's what you said, unless something X on.
Yes. Yes. If another force acts on her, then her velocity would change.
Is that what they're talking about, where it says until another force?
Yes.
I thought you said that was incorrect.
No.
Friction's there.
Friction. If we say friction slows her down, that's what the original statement said. That's not true. Because friction wasn't a part of the scenario.
I was looking up the wrong.
So they're affirming, hey, friction's neglected. That was part of the problem statement with a frictionless skateboard.
So friction,
That's why it wouldn't slow down. Aiden?
so friction wouldn't slow her down, but the highway she's rolling too low.
If there's a car that would hit her, yes. This is getting really dark.
What
They already go dark when it says a wall.
It's dark.
What?
I wasn't listening. You said it was dark. But
Aiden's was like, well, if we say no friction, then the friction doesn't slow her down, but the highway that she eventually rolls onto would.
oh,
And I was like, well, yeah, I guess if she gets hit by a car.
Or she hits a car.
if she
Yeah.
Like she just like T-bones a car. I was gonna say.
Yeah.
What speed would you have to be going just to keep the motion fluent?
What do you mean? Keep her motion?
Okay, so she's going particular velocity, right? At what speed would a car have to hit her to just keep her at the same velocity going in the other direction?
To exactly flip it?
Well,
So like velocity 10 meters per second this way and then go 10 that way?
I'd say
Is that what you're
velocity
saying?
Like,
Acting like she will get like pushed off of her skateboard.
Yeah, kind of like how when on that one lap where they shot the person out of the cannon, and instead of them going splat, they just popped right up. So theoretically, in a world where she doesn't go splat across the car,
I'm
John
not
is
sure
saying like how much force would
what's
it
the
take for her to just like reverse?
and for velocity,
I don't know.
If for
Be-
velocity,
Because
it's
it would
like
have to
10.
hit 0 and then go. Oh, you have to stop.
Because in that collision, this car would have to be going really fast. Well, depends on the mass. See, you're getting way ahead because that gets into momentum and kinetic energy, which we're not there yet. We will talk about how you would answer that, and it's a pretty simple answer, but we need to know momentum and kinetic energy. And we'd also need to know the mass of the two objects, which I don't know. Evan?
Can I use the restroom?
Yes, quickly.
car. Yeah, ton of two.
Alright, does this make sense?
Yeah.
Again, I just wanted to run through that. The next thing I want to do, I want to finish our notes here. I want to finish these today. Oh, dang it. I don't want to start from the beginning.
Answer
Current slide. Oh, you little. There. Okay. So you guys remember
by a Ferrari.
these slides? This is Newton's second law. F equals ma.
Yeah.
Remember, there's 4 relationships that we can get from this equation. One of them was that acceleration is proportional to 1 over mass. Increasing mass decreases acceleration. Acceleration and force are directly related. More force on an object, more acceleration. To have more acceleration, I need a lot more force. The acceleration can only be 0 if you have no forces. You can't have an object with 0 mass. 0 mass means 0 matter, aka it's not an object. Yeah, it makes no sense. The only way to get 0 acceleration is if there's no forces. That makes sense, right? The last relationship was acceleration and force are vectors. They have a magnitude and a direction. Mass is a scalar. It's just a number. Whatever force, direction you apply that force, acceleration happens in the same direction. That's how these two equations can be equal. My vectors have to equal, meaning both the magnitude of them and the direction. Well, the magnitude's altered by the mass, but the direction, whatever my force is, that's where my acceleration happens. All right? If you have a 5 Newton force, that creates a 10 meter per second squared acceleration. If you double the force, what happens to the acceleration? Yeah, you got F equals ma. If I double the force, I put 2F. The mass does not change. It's the same object. How do I keep this equal? I need to have 2A. That's how I keep these equal. I need this law to work. So double the force, double the acceleration. What happens if you have this aircraft? There's 4 engines. When it takes off, it can accelerate at 2 meters per second squared. If one of your engines fails, what's your new acceleration?
On
It's
the
hard because you die.
Well, I heard like 4 answers. What? One by one.
1.5.
1.5? Why did you say that?
Because it's going 2 meters per second. Divide amongst the 4 engines.
Okay.
One just goes out.
Well, wait, it never said that all 4 engines are running. Maybe
said
only
you
2
just
engines
die.
are running.
You're true. Let's say that the aircraft has 4 equal engines that are all operating. Then, would John be correct?
Yes.
Yeah. 4 engines they each produce a fourth of the force. If I lose one of them, I lose a fourth of the force that I could provide. Force and acceleration are directly proportional. So I lose a quarter of my acceleration. So John's right.
I feel like 2 meters per second is extremely slow
Yeah.
for an aircraft.
I mean, I hate being in the U.S. because we use the English system. John, can you look up 2 meters per second squared converted to, or do 2 meters to,
But this is the takeoff speed, right?
miles? So yeah, it would be slow. Do meters per second to miles per hour.
Meters per second squared.
Yeah, you see here,
Okay.
fully loaded
It's saying-
747 usually takes off at 180 miles an hour.
That's 4 miles.
What? No, it's
2 meters per second is 4 miles an hour.
is it meters per second squared?
But we want to know the speed. If we know if 2 meters per second is 4 miles an hour,
Yeah.
so then it changes by 4 miles an hour every second. So 4 mile an hour, then 8, then 12, then 16.
Yeah, that sounds.
Yeah, it's slow.
Yeah, because 184 miles an hour would translate over to 82.255
Seconds?
or meters per second.
Yeah. So that's good. So this is a very slow acceleration for an airplane.
I don't think
It's
that-
not realistic.
I don't think you want to get off the ground. I mean, unless the paper airplane.
Well, yeah, less than 6
Yeah.
That might take you a little longer to get your
So when are you accelerating at 180 miles per hour?
Well, I looked up. I like the takeoff speed because that thing was taking off. So
Yeah, but it said that was the acceleration was 2 meters per second.
If
the
it-
acceleration was 2 meters per second.
Yeah.
Oh, okay, misunderstood. I thought I was saying that's what the speed it was going. Like,
No.
I
okay.
don't think it's accelerating fairly slow.
Yeah, it is slow. Anyway, that was a good question, but I want to move on.
Well, one thing is not.
That's 50 pounds.
170. Is that what the right place?
Yeah, here. What's the net force on that fridge? If the velocity is 2 meters per second, or 2 mile an hour. First question, does my velocity change?
No.
No. It said it was 2 mile an hour the whole time.
Yeah, that fridge pretty counts.
When I push this, friction opposes me.
So,
In this case, real life, friction opposes motion. If I push with that force, the friction between the fridge and the floor is exactly the same. If those forces are equal and opposite, what's my net force on the fridge? Consider the direction. 50 and 50. What's positive 50 plus negative 50? 0. My forces literally negate each other. So even though I'm pushing, it's moving, but it's not accelerating. My force and the friction force cancel out. There's literally no net force. That means there's no acceleration. That's why I have a constant velocity.
That guy looks like the logo from a pizza restaurant.
Oh, this one. Rocket, it's being accelerated by a force, right? This jet engine is shoving back and pushing the rocket forwards. So this force is pushing the rocket forward. Immediately, there's another engine that, like, say, appears exactly opposite. What happens to the ship's motion? It either comes to a rapid halt, it will very slowly come to a stop, or it will continue at the speed it had just before the second force began. Gotta vote for B.
Doesn't depend on how fast the other engine's going.
Both engines are going in the same direction.
Both engines,
Oh, I thought you meant like if
this
it's
engine
opposite direction.
appears here and pushes exactly opposite. Like this. So all of a sudden, that engine's shoving, applying a force, it's accelerating it. Then you have another engine appear, equal and opposite.
Stops the acceleration and you're in space, so I think it'd be C.
Ethan said in C. What else do we think? We got a B. Aiden? B.
C.
Let's use F equals MA.
Wouldn't you just crush the plane?
I feel like it would just crush.
Before I have force, rocket
Let's go.
equals mass times acceleration, right? This thing's accelerating into space because that rocket's shoving it. When I have that other engine show up, don't I have force rocket minus force rocket? It said that force is equal to the original force, but in the opposite direction. If I have two forces going in the opposite direction, one's positive, one's negative, they're the same number. Doesn't this go to 0? I still got my mass. What does that mean my acceleration has to be? 0. The moment that engine appears, I stop accelerating. Even though I have two forces, they completely cancel each other out. There's no force, no more acceleration. Well, I was already going a certain speed. Do I stop? No, that's an acceleration. There's no way that I can change my motion, so I'm stuck at whatever speed I was right before the engine hit. Right? I think there's a graphic. So it's going. Eventually this will turn on.
Yeah.
Your velocity stopped changing because you stopped accelerating. Right? F equals ma. The moment you took away that force, you have a force. It's accelerating. It's going faster and faster and faster, and then boom. I cancel out the forces. There's no actual force acting on it anymore. They cancel each other out. Well, if that's the case, I can't change my velocity anymore. Looks like I'm stuck going that speed forever.
Is that why I'm like stuck whenever like cars run directly at each other? When it makes contact first, keep going.
Sometimes. That's amazing because that question, again, is momentum and kinetic energy. So the answer to your question depends on the speed of both cars and the mass. If you have more mass, you have more energy. If you have more speed, you have more energy. We're going to answer that question by looking at whose car has more energy. Whoever has more energy will win and keep going and plow through the other one. That's why if you have, say, your Tahoe, remember my example about the smart car? You got your little smart car and your Suburban, huge. They're going the 60 mile an hour. Same exact speed. Who has more mass? Tahoe. Way more mass. Even though they're the same speed, I have more mass. That gives me more energy. And in that collision, my greater energy overcomes the other car. That's why it keeps going. And again, we're going to get into the math of exactly how I figured that out. Now we're looking at acceleration and force in the same direction. If I hit the gas, I'm pushing my car forward. Guess which way it accelerates? Forward. That should be obvious, right? When I hit my brakes, I clamp those brakes and I stop my tires from rotating, and they start rubbing on the ground, creating a ton of friction. That points this way. My acceleration is this way. It means you're slowing down. My velocity it decreases in this direction. Right? My brake pushes back on my car, and so my acceleration slows me down. Right? If you have a ball, you let it go. The only thing acting on it, right? Assume air resistance isn't a thing. Gravity. Right? That's why when you throw something up, it comes right back down. Gravity accelerates it this way.
Are you sure about that?
Huh? Yeah, physics still works, right? We didn't break physics quite yet. Ooh, this one's cool. It's a Mission Impossible scene. We're going to critique the physics.
We're gonna have to watch all the Mission Impossible.
Now, I don't have the sound, and I don't want to hook it up, but...
We're going to have to watch the whole movie to get the context.
Oh, you're right, context. Missile, airstrike coming in.
Which one is this?
This is, I think, 3.
That's what I thought. I thought it was 3.
We're going to see Tom Cruise run again. He's a great runner. Right here.
Why did you go to the side?
Haha, that's a great question. Did you guys see that?
Explosion this way, you go this way.
Yeah, Andre's like, what the, why did he go to the side? The bomb was behind him.
That's weird.
And he goes this way.
By the editor.
It's baloney.
If anything, you should have went to the wall.
It's total crap.
Wait, did you notice though when the car was hit, the flames kind of shot out like that way? So maybe the explosion.
This way?
Yeah.
Roll tape again.
So
Technically,
roll back because like when the thing hits, the car also explodes because the vehicle is probably gasoline. So watch when it hits.
Kind of screwed up.
Yeah.
but the problem is, I get what you're saying. Explosion, it does go outward in all directions. But he's in front of it. The explosion is happening behind him, and somehow he goes this way. That's what's missing. Technically, he should have gone like this. If the explosion's behind him, but it radiates all ways.
So he shouldn't have gone like 90 degrees this time.
Actually, no, he should have gone straight.
Yeah.
If it's directly behind him, the explosion goes in all directions.
So it's
Well, if I have some force in this way and some force in that way, they cancel each other out. The only force that acts on me is what is straight at me, because there's nothing to counteract it. So that's why this scene is baloney.
So if you're going straight at the explosion, you counteract it.
Watch it. It's
Wait,
when you see it, it's like ridiculous.
When he hits it like that, with the back
You
of
see all
that
the
car.
I
flames?
was gonna say the middle of the back window
So if you run straight-
Yeah, look at that. When he hits the car, the middle
He
of
hits
the
the
back
side
window
of the
just
car,
shatters.
and then the middle of the window
They probably shot something out of it.
So if you run straight at the explosion, you're counteracting.
Yeah, it could. So one,
Even then, it probably.
if you're like me, sometimes this ruins movies for me because I can't shut my physics engineering mind off, and I like literally will watch a movie and I'll just go because it's ridiculous, right? That rock scene where he's holding 5 cars in a helicopter with his arms. I literally just start laughing.
He's pretty.
Wait,
No.
what
There's
about-
literally no way possible. He would be ripped apart.
So if
Yeah. So one, I hope this, as you learn physics, I hope it doesn't start ruining movies for you. To me, I don't think of it as ruining, but I critique it. My wife's like, Austin, shut up. Just watch the movie. I was like, Vaughn, this is ridiculous. And I can't stop laughing at it. And that's why. Again, you have the understanding to think about, here is my force, here was my acceleration.
No, that seems perfectly normal.
Yeah, it totally makes sense. No, it violates Newton's second law, right? The only vectors are your force and your acceleration. They have to be the same. Otherwise, this movie apparently broke physics. Right, Brody?
I have a question.
Yes.
You know how you said the explosion goes off in every single direction, and you said that these will cancel?
Yep.
So if you're somehow physically possible, you're able to run at the explosion with the same amount of force it is pushing off against you, would that cancel out too?
You can't
Yes.
stay there.
Yeah, it would be with the, yeah. If you ran at the explosion and you had the same energy that the explosion gives off, you would literally just stop.
It'd be hilarious.
Like you would be running, and if say you were in midair and the explosion went off, the forces would literally cancel each other out. Actually, no. I misspoke. Why was my statement wrong?
Because the
Bro-
forces are equal, so when it just keep going at the same speed.
Yes! I told Brody, I said, if you run at an explosion with the same force as it explodes at you, I would say you would stop still. That is not true.
Why not?
I'm running at a certain
Rocket
speed,
problem we just did.
and the force negates my force. That stops acceleration. That doesn't change my velocity.
Accelerate, you're just going at a constant speed.
Well,
Because he's saying you're going at the same, like with the same force as the explosion, so you wouldn't be accelerating because the explosion wouldn't be accelerating. Like you didn't you know what I'm saying?
okay.
If the explosion would explode, it wouldn't explode and then like.
I get what you're
like
saying.
a big,
You're right. If I'm at a constant speed, you again would have to go to momentum and kinetic energy. So I get your point. And I'll, again, clarify that you're right. If, say, I was accelerating with that force and then the bomb goes off, Brody's right. It would cancel forces out and I would just be stuck at whatever speed I ended with. Now, Josh was saying if I'm running at a constant speed already, my forces are already balanced. So when that explosion hits, it would accelerate me this way. Now, what that would mean is it would slow me down. It might slow me down exactly to where I stop. If that force is huge compared to like my mass, it could stop me and start sending me backwards. But that you have to pull in momentum and energy. So that's a great point. I appreciate that. Good questions.
What do I have left?
Not a lot.
We can be done, right? We had good discussions.
Oh, and if I did on that.
Oh. The last thing I want you guys to do, look up do 2C. I don't think we'll finish it right now. This is important. This is a big concept that we're going to start looking at called a free body diagram. Have you guys heard of that before? A free body diagram. This is a huge deal in AP Physics. They're very particular about it too. So they have like very clear rules on free body diagrams. So what a free body diagram, the first rule, you're going to draw typically a dot is ideal. Sometimes you can draw a box, but this is the object, right? This is the system. You're basically going to draw it as if you remove it from whatever situation it's in, and you think, hey, this point is in free space. What you add in are the actual forces acting on that object, but we draw them as explicit arrows. So in this case, you push a block across a ground that has friction at a constant speed. Well, one, I'm pushing it, aren't I? That is this, F sub P, the force of pushing. I need to draw that and say I'm pushing it in this direction. That force is acting on that object in this direction. What else acts in the X direction? The friction. The friction opposes motion. Friction always opposes motion. So you need to draw, hey, Friction causes a force on that object. The length of your arrow has meaning. Why do you need these to be equal to each other?
Because friction is always opposing equally.
Not always. But in this situation it is.
Most.
Constant speed.
Yes.
There's no net force. These are equal and opposite, right? Plus 5 and negative 5 add up to 0. I know that has to be the case. So when you draw this, you have to draw these arrows the same size, aka the same length. Right? It's a vector. Your arrow needs to show me the side or the direction, right? In this direction. Your arrow also needs to show me the magnitude. Well, I need to draw these equal lengths, but opposite directions. It's very, very important that you understand that. AP makes a big deal about it. The length of an arrow represents the magnitude, how big the force is. What's this force? F sub g. Sorry if you can't read it. I can't zoom it in anymore. F sub g
Probably gravity.
is gravity, right? Even though it's on the ground,
I agree.
gravity will always be acting on objects. Why isn't that object going straight to the center of the earth? What stops it?
The ground.
The ground. Now, you haven't talked about this yet, but this is that normal force. I don't know who I was talking about that. Normal force is just a force where the ground pushes back up on you. I'm standing on the ground. Gravity's trying to push me down. The ground is supporting me. Gravity and the normal force are equal and opposite. That's why I can stand still and I'm not accelerating any direction in the y direction. These have to be the same length. There's no acceleration in the y direction, so all of my forces in the y direction have to be equal and opposite in order for you to have zero force and therefore no acceleration. Right? You always label your forces. Right? Fg will always be gravity. Sometimes they put it like Fmg, mass times gravity. This is the force of gravity. F sub little f, right? Capital F and little f is friction. This one you can make up, like it was a push, so I called it F sub p. But you label and describe what all the forces are. You also need a coordinate system. This one is technically missing a coordinate system. But this one you would need to put... Technically you would need this. Now I'm not going to nitpick this a ton. Almost always, anytime you draw it, you're going to draw it as if x, y. If you draw it on an incline, you tip your drawing. So it's fine. This is still y, this is still x. The other thing, the only exception to drawing it this way, you could draw it like this. Right? I could draw a box. That's my object. And I could say, this pushing force acts this way. Instead of saying it pushes, it starts at the object and goes in this direction, you could say it gets applied right here. If you do it this way, you have to do it for every single force. You can't mix and match these. All the forces either need to come out of the object in whatever direction they're going, or they all need to go on the object. Friction would go here. Where would gravity go? On the object. Normal force.
I like that one better.
Yes, this makes more sense to me.
Yeah.
To me, this means this force literally gets applied right here. Well, that's true. The bottom of my shoes, that force pushes up. Gravity, it acts on my whole mass, but I think about it, it points at my head.
Yeah.
Right here. When I push on it, I'm pushing right here. My force is applied literally right there. Friction is a little weirder. Friction technically acts like right here, but you can't draw it like that.
Because that's
So this is going to sound really petty, but it's because it is. You have to draw, typically you draw a dot, or you can draw a simple box. That's a good free body diagram. You have to pick how you draw forces. Either this way or that way. Never mix the two. You also never draw components of a force. If I have a force like this, like this, if I'm pushing up on it, I need to draw that as the force that's acting. I would never draw the components. You never do a component of a force. You have to draw the actual, real forces that act. Once you have your free body diagram, I always draw a second one where I draw all the components so that I can do my math. But a proper free body diagram only has real forces. And again, a force is a magnitude and direction. Your drawing of a force has to show magnitude and direction. So I don't mean to be like overly critical. It's just you have to get it right. You have to get it right the first time. Otherwise, it'll mess you up over and over. Because AP, on an AP test, if they have you do a free response, and they want you to draw a free body diagram, they will want exactly this. No exception. All right? So no homework. We'll come back and we'll do, I think, Newton's third law. Okay, thank you guys.
And if I did my math right, the acceleration speed for that plane would be somewhat accurate. Because it said
Really?
it said for a Boeing 747.